everybody, my name is Kiran. I am working as an assistant professor in the Department of EEE Anits. I welcome you all to my 7th lecture under the first module of DC generators. In my previous lecture, I discussed the concept of armature reaction and how the armature flux has affected the main distribution of the field flux. So in today's lecture, we are going to see what are the various effects associated with armature reaction and what are the remedies that we can find for armature reaction. The first coming to the main effects of armature reaction. So we have two main effects of armature reaction. First one is the net reduction in main flux, that we call it as demagnetizing effect, and second one, the main field flux gets distorted, and this we call it as cross magnetizing effect. So due to demagnetizing effect, we further have two effects. One is reduction in generated EMF and increase in the cost of field winding. Due to cross magnetizing effect, we have three effects. First one, the iron losses increases. It leads to poor commutation and it also leads to sparking. So we'll see in detail one by one what are the effects of the armature reaction. So coming to demagnetizing effect, the first one we have seen is the reduction in generated EMF. We know that Eg is P5Zn by 16 to P by A. So as Eg is directly proportional to flux, as due to armature reaction, your net main flux is getting reduced. So due to which the generated EMF will also get reduced. The second effect is increase in cost of field winding. So due to this demagnetizing effect, as we have seen that the total net resultant flux gets reduced. So due to which the magnitude of generated EMF also is getting reduced with increase in load. So in order to compensate this decrease in magnitude of generated EMF and resultant flux, we compensate this reduction in flux by adding extra number of turns in the field winding, so that this reduction in flux can be eliminated. So but in order to compensate and in order to increase the number of turns, we know that more copper is required and the cost of field winding will also increase. So these are the two main effects due to demagnetizing effect. Coming to cross magnetizing effect, so under that the first effect was it leads to increase in iron losses. We all know that the losses depend on the maximum value of flux density, and since the armature reaction is distorting the main flux, it also increases the flux density. Okay, when I go to the diagram, you can see this is the distribution due to armature reaction. See, you can see this is the distribution of the flux when there was no armature reaction. So the distribution is very uniform. So this is the waveform for flux density, okay, or you can say flux or flux density. Okay, so when the armature flux is playing a crucial role in the DC generator, as it is distorting the main flux, you can see how your waveform is getting changed and the maximum value of flux density is increased. As you can see from the diagram, the maximum value or the peak value has increased. The zero crossing also gets shifted by some angle. So these are the two main observations that I can see when regarding the waveform of flux density. Coming back to our topic, so you can see that the flux density magnitude is getting increased, and since losses are depending on the maximum flux density magnitude, obviously the iron losses will be more, and particularly the losses will be more at load when compared to no load. roughly at full load the iron losses will be around 1.5 times that the value at no load. Coming to my second effect due to cross magnetizing effect, as I have shown you in the diagram, the at no load the zero crossing of the flux density wave was along the GNA, but after the armature has been loaded and due to armature reaction, the zero crossing of the flux density waveform has been shifted by an angle. You can see clearly this shift in the zero crossing. Previously the zero crossing was here, now it has been shifted to here. So this angle change will lead to poor commutation. Okay, commutation is nothing but the process of reversal of current, and that is what we have seen. The zero crossing of flux density, since it is changing, it also affects the process of reversal of the flux. Okay, so this is the second effect, and the third effect, if we see, it leads to sparking. So due to this poor commutation, MNA axis has been shifted, as you have seen in armature reaction. So MNA axis, after it gets shifted, the brush should always be along the MNA axis. Okay, previously GNA, when GNA and MNA were coinciding with one another, the brush was also along the GNA and MNA. But due to the armature reaction, since the resultant flux MNA axis has been changed, the brushes, we need to change the position of brushes now, because if we don't change the position of brushes and if we still keep it in our previous position, it will lead to sparking. Okay, so that is the third effect of cross magnetizing effect. So sparking will occur at the brushes if you do not shift these, if it does not coincide with my MNA axis. So these are the effects due to armature reaction, and what can we do in order to eliminate these demagnetizing effect and cross magnetizing effect due to armature reaction. So let us see what are the remedies that we can see for armature reaction. The first remedy is using high reluctance pole tips. Chamfered pole face is used, so due to that the air gap will be short in exactly in midway, and near the edges the air gap will be long. So that is one way of reducing or maintaining high reluctance pole tips, thereby reducing the flux density. So as I told you, by doing that the reluctance is increased and the armature flux magnitude gets reduced, thereby the distortion of the flux density waveform is also minimized. So the second method is shown also by how we can increase the reluctance is by assembling the pole laminations alternatively in the second diagram, as you can see. By doing so, the iron area under the pole tips is getting half, so thereby the reluctance will increase. Okay, so these are the two ways by which I can increase my reluctance of the pole tip. First one is by using chamfered pole tips, which will have shorter air gap at the center and longer air gap at the tips. And the second method is by assembling the pole laminations alternatively, thereby decreasing the iron area under the pole tips. Obviously that will increase my reluctance. This is the first remedy. The second remedy is by using field pole laminations with punched holes. So you can see there are holes present in the field pole laminations. So this is one way of reducing the armature flux, because by doing so what will happen is we are introducing air gap in the path of the armature cross flux. So by introducing extra air gap, the reluctance is increased. So since the reluctance is increased, as a result the armature cross flux will decrease, thereby the distortion of the main flux also remains almost unaffected. So this is the second remedy of how to reduce the armature reaction. My third remedy is by maintaining strong magnetic field. So since we have two field, one is armature flux and another one is main field flux. If we ensure that the main field MMF is very much greater and strong when compared to armature MMF, then that distortion that is caused by the armature flux will not have or will not show any significant effect. Okay. And the fourth method or the fourth remedy is by using interpoles. So from the diagram you can see the interpoles are placed in between the main poles. So and the winding is connected, the interpole field winding is connected in series with the armature winding as shown in the diagram. So one should remember that the polarity of the interpoles must be of that pole which is ahead of it. That is, if I take this diagram, so if I consider this interpole, so ahead of this pole, since I have a south pole, the polarity of this interpole should also be south pole. Okay, when I consider this interpole ahead of this interpole is north pole, so the polarity of this interpole should also be north pole. So the polarity of the interpole will be what can I say, can be decided by the polarity of the pole that is ahead of it. And as I told you that the interpole winding is connected in series with the armature winding. So this is because interpole will set a flux in such a way so as to oppose the armature flux. So both will respectively fall and rise simultaneously, cancelling the effect of armature reaction. But this effect can only be seen greatly in small machines. Okay, for larger DC machines the interpole will not that much considerably neutralize the armature flux. So this method or this remedy is only applicable for small DC machines. And the last remedy is using compensating winding. So here compensating winding, so since in the previous case we cannot totally nullify the armature flux using interpoles for large machines. This method is greatly used for larger machines to eradicate or nullify the armature reaction. Here these compensating windings are placed, as you can see, in the face of the field poles, and the windings are connected in series with the armature winding such that the current in both are opposite to one another. Under the pole phases, the compensating winding MMF will neutralize the armature winding MMF. See, since they are compensating the armature winding MMF, the main flux distribution will not get distorted. Okay, so this is one of the effective ways to eliminate or nullify the armature reaction in large DC machines. So this concludes my today's lecture on the remedies as well as the effects of armature reaction. So until we meet with the topic in the next lecture, take care, thank you and goodbye.